Uh, Binary tree is a very special kind of data structure which is heavily used in day-to-day applications. And if you are writing a very efficient code with good data manipulation, binary tree provides you very good platform to solve very complex problems. So let's begin with binary trees. So in this session we are going to cover about what are binary trees, what are terminology that we use in binary tree, what is meant by size and depth of a binary tree, what all are balanced binary trees. Then we will be covering about a special kind of binary tree which is called binary search tree. Then we will be covering about tree traversal and what are the structure we used in binary tree. So binary tree, so that you can go ahead and write a code for a binary tree. So let's begin. So what is a binary tree? A binary tree is a composed of zero or more nodes. In C, reference to a binary tree may be null. So binary tree is something like this. So any node has two references. So suppose this is a node, okay. uh, this node has two references. One is the reference to left part, one is the reference to right part, and this is a data section, okay. So binary tree is composed of two or more nodes. Here we are having two nodes. One is for left reference, one is for right reference, okay. Each node contains a value, a reference or a pointer to left child, a reference a pointer to right child. So whatever be the reference that it has towards its left, this is called the left child of this node. Whatever the reference this node has towards the right, so this is called the right child of this node, okay. And if any node is there with no reference, then it is called as the root node, okay. So we always start with root in the binary tree. Then each node in the binary tree has two references, one is left, one is right, and we keep on building the tree. A binary tree may be empty. So in case if binary tree is empty, then this node will be null. So if root is null, that means binary tree is empty. If not empty, a binary tree has a root node. So if not empty, this will have some value, and whatever value it has, this will be called as a root node. Every node in binary tree is reachable from root node by a unique path. So every node in a binary tree can be accessed by root node through some unique path. For example, if you want to go to H from root, the only path you can go from here, root to H, that means A to H, is you need to go from A to B, B to E, and E to H. There is no other path that you can go from A to H. There is a unique path from root to every node. A node with no left child and with no right child is called a leaf node. So suppose there are any nodes with no left child and no right child, for example like this. So it does not have anything on the left, does not have anything on the right, so this is called a leaf node, okay. So in binary tree, what all we have a root node which does not have any reference upwards, okay. And then for any node we have a left reference and right reference. The left reference is called the left subtree, right reference is called the right subtree. There is a unique path from each node from root. So if you want to go from root to any node, there is only one path. And if any node which does not have any left reference or right reference, then it is a leaf node. So this is a very basic binary tree representation. uh, and as and when we proceed, you will be able to understand these concepts more and more in depth, and this will give more understanding on what are binary trees. Okay, so let's continue with further explanation on binary trees. So in binary tree, the following two binary trees are different. So suppose this is a node and this is one more node. Both node has same values a and b, but these two are different binary trees. Why? Because here in this case b is the left child of a, okay, but in this case b is the right child of a. So the representation of a tree in this diagram and representation of tree in this diagram is totally different. So hence we call it as a different binary tree. If the first binary tree in the first binary tree, node A has left child but no right child, correct? So it has left child but no right child. In second, node A has right child but no left child. Put in another way, left and right are not relative terms. Yeah, so left and right are not relative terms. You cannot just do some relation between left and right. So binary tree terminologies. Node A is the parent of node B if node B is the child of node A. So what is mean by parent and child? In this case, node B is child of node A. That means in hierarchy, node A comes first and node B comes after A. So A is parent of B and B is child of A. Node A is ancestor of B if A is a parent of B. So another thing is also called as node A is the ancestor of B. So whichever comes first from the traveling from the root will be the ancestor of the node which comes after that node. So A comes first and B comes after A, hence A is the ancestor of B. Node B is a descendant of A. So similarly B comes after A, so B is the descendant of A. Node A and B are siblings if they have same parent. So if A and B are having a same parent, like suppose there is a node called C here, okay, let's say C is here, then B and C will be siblings because B and C will have same parent called A. So let's cover about what do you mean by size and depth of a binary tree. So suppose this is a binary tree. The size is the number of nodes in a binary tree. So here in this case, number of nodes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the size of binary tree is 12. Correct. The depth of the binary tree is the node to its distance from the root. So A is at depth 0. So because since A is the root, so distance from root to root is 0. B is at distance 1. C is also at distance 1. E is at distance 2. H is at distance 3. So E is at depth 2. 0, 1, 2. This is the second depth. Also you can say number of hops that you need to do while reaching from to a particular node from A or root. So if you want to reach E, how many hops you have to do? 1 and 2. So 2 hops you need to do. So number of hops equal to the depth of a particular node. The depth of a binary tree is the deepest node which is present in the binary tree. So if you say what is the depth of this tree? So depth of binary tree is the depth of the deepest node. So here in this case, L is the deepest node because L is at the bottommost position. Okay, so what is the depth of this tree? Depth of the binary tree will be equal to depth of L, and what will be this value? Let's hop it from A to L. 1 2 3 4. So the depth of this binary tree will be 4. Okay, so what is a balanced binary tree? A balanced binary tree is in balanced binary tree, if every level above the lowest is full. Okay, so suppose this is the last level of a binary tree. So if every level above the last level is complete means every node has two childrens. So suppose this is considering this example, the level above this row is this row. So if this row is complete, say B and E, C and G, okay, and so this is called balanced binary tree. This is called unbalanced binary tree because the level above the lowest is not full, because again if you can see here, A is the root but A does not have anything on the right, so we cannot balance, we cannot, this is a balance, this is balanced because uh, all the nodes are present at the left of the tree, there is nothing present at the right of the tree. So there is one more concept in balanced binary tree, is that the left the height of the left subtree and height of the right subtree should not be greater than 1. Okay, the difference between height of left subtree and height of right subtree should not be greater than 1. It could be equal to 0 or 1. It should not be greater than 1. So what is the height of left subtree in this case? A is the root. The height of left subtree is height of B, which is equal to, we need to go from B to I. So 1 2 2 hops. Okay, so height of left subtree is 2, 1 and 2. What is the height of right subtree? Height of right subtree is also 2 because J is the deepest node, and subtree starts from C. So C to J will be covered in 2 hops, 1 and 2. So hence it is balanced binary tree because height of left subtree and height of right subtree are equal. Now in this case, height of left subtree is height of B to I. Okay, so what is the height of height from B to I is 1 2 3 4, and but at the right there is no right subtree, so the height of right subtree is 0, and the difference between height of left subtree and height of right subtree is 4 minus 0 equal to 4, which is greater than 1. Hence this is not a balanced binary tree. So there are many ways to find whether a binary tree is balanced or not. I have just explained two ways, and this concept is very important when we solve some few problems. It is in most application a reasonably balanced binary tree is desirable. So binary tree will become more efficient if it is balanced. If it is not balanced, then it is as good as a linear or linked list. Because if suppose every node is at the left child, every node is at the left of the tree, then it becomes a list kind of structure. It will not become a tree kind of structure. So to make more advantages, or to take more advantage of a binary tree, make sure that your binary tree is balanced. Okay, let's cover out about what is binary search tree. Binary search tree is a special case of a binary tree where each node has two children, left and right, and the value of left children is less than the value of the parent node, and value of right children is greater than the value of parent node. So this is the property of a binary search tree, and it is very helpful while doing searches because it reduces the number of times we need to iterate through the tree. Okay, so uh, let's see what is binary tree in picturization form. So this is a binary tree where each node has at least or at most two childrens. Yes, any node has at most two childrens. Okay, and value at the of the left child is less than the value of the parent. Yes, value of the left child is less than value of the parent. Value of the right child is greater than value of parent. Yes, value of the right child is greater than value of parent. And so there is one more important property in binary search tree is not only the immediate nodes but the left subtree or the right subtree is aligned according to value. So every element or every value in the left subtree will be less than 10. So here whatever value is there, however tree grows, the value at the left subtree will always be less than 10 and the value of right subtree will always be greater than 10. So this becomes kind of a balance. Okay, and how it helps to do the search we'll see just now. So also, if we traverse through a binary search tree in a particular manner, okay, we will see touch about how to traverse in a tree. But if we traverse a binary tree in a particular manner, it will always result in a sorted array or sorted form. Okay, so this is also very helpful. We will see how it is helpful to us. So binary search in a sorted array. So let's assume we have an array and say this. Okay, now look at the location of this array, which is low is the lowest element, lowest index, high is the highest index. So lowest index is 0, highest index is 6. So 0 plus 6 by 2 equal to 3. So 3, if we calculate this, we will get 3. So searching for, so 0 plus 6 by 2 equal to 3. Okay. Now what is the now we divide this array into two parts, this part and this part. That is, this will become root. Okay, and this will be the left subtree and this will be the right subtree. So now when we build the left subtree, how we build? uh, Low is 0, high is 2, low plus high by 2 equal to 1. So 1 will become the child of 3. Okay, left child of 3. Now let's again do one more round of iteration where low is equal to 2, high equal to 2 and low plus high equal to 2. So 2 will become the right child of 1. Okay, so using same approach we can build this array in form of a binary search tree which will look like this. So since we got the first element as 3, as at an index 3, so the value at index 3 will become the root. Okay, so 7 will be the root. Okay, now all the elements at the left, uh, all the element which has index less than 3, these index 0 1 2 will come at the left side of the tree. All the elements which has index greater than 3, that is 4, 5, 6, will come at the right side of the tree. So now we remain with this sub array, small array. Now to create, now to find a root in this sub array, we will again follow this same method, low plus high by 2. Here low will be 0, high will be 2. 0 plus 2 by 2 equal to 1. So 1 will 1, or the position at 1, which is equal to 3. This will become the left child of root node. So 3 will become the left child of root node. Again we follow the same approach, low plus high by 2. Then we get 5 will become the right child of 3, 2 will become the left child of 3. If we follow the same approach here, we will get this kind of a structure. Okay. Now how this structure is helpful in searching? Suppose we want to search for 5. Okay. Now we will see, now we will compare 5 with root. So 5 is less than 7. So definitely our 5 is not at the right side of 7. It will be at the left side of 7. So we will traverse left. Traversing left, what we find? We find 3. So what if we compare 5 and 3? 5 is greater than 3. That means we need to go at right, because every element at left of the tree will be less than the root element, and so we there is no way where we can find at the left side. We have to go at right side. Going right, we can find 5. So how many iterations that we need to do? We need to do 3 iterations. Let's suppose we need to find say 13. Okay. How we can find how we can find value 13? We just have to compare it with the root node. So 13 is greater than 7. Yes. So there is no way where we can find our solution at the left side of the tree. We need to go at the right side of the tree. Okay. We need to go at right side. Now going towards right side, what will be the value we got? We got 13. Yes, we find 13. So how many iterations or how many comparisons we need to do? We need to do only 2 comparisons to find 13. 1 and 2. Okay. If suppose we have to do a linear search where we just have to iterate through the list and find out a particular element, how many iterations or how many comparisons we need to do? We need to do 1, 2, 3, 4, 5, 6, at least 6 comparisons we need to do. But here in 2 comparisons we are able to find out our result. So this is how binary tree is very helpful in searching technique, because it reduces the amount of comparisons or amount of work that we need to do to search a particular element, or it will also tell whether a particular element is present or not. So for example, suppose we want to search say 15 in this. Okay, whether 15 is present on this binary tree or not, we just start with root. 15 compared with 7, 15 is greater than 7, so we need to go right of the tree. Going right of the tree, we find 13. Comparing 13 with 15, we found that yes, 15 is greater than 13, so we need to go further right. Further right we found that okay, 17, 15 is less than 17, so we need to go left, towards the left of 17, but there is nothing towards left of 17. We reached till the leaf of the tree, so there is nothing at the left of 17. So that means our element that we are searching, which is 15, is not present in the tree. So we can say okay, our whatever we are trying to find is not present in the tree, and we can and we did it with how many comparisons? 1, 2 and 3. If suppose we need to find this in a in this array, how many comparisons we need to do? We need to do at least 1, 2, 3, 4, 5, 6, 7 comparisons, because we need to traverse till the end of the list to find out whether our uh, element is present or not. So this is how searching in binary tree works. So before going to the coding part, let's see how binary tree is represented. As we have seen in the linked list, binary tree is also represented in a structure format where this is the data part, this is the reference to the left, and this is the reference to the right. Okay, this is a very basic node structure of a binary tree. Uh, Going towards more enhanced way where we have some advanced kind of data in the data section. What we can have is we can declare one more structure called data where we can store whatever we want. Okay, and then we can have left reference and right reference. So this is how we can represent nodes in binary tree. So let's do some problems. So this is a program where we represent binary trees. Okay, so what we are doing is here I am including stdio.h, stdlib.h. This is a structure for binary tree where we are having a data portion, reference to the left node, reference to the right node, type defing it with tree node, so that we don't have to use struct node, and tree node is very self-explanatory. We are having a function called add node, which is just adding a node to the binary tree. Okay, so add node will return a pointer to pointer type tree node, and this will add node at, we'll be passing root here, and it will add the value to the left to the node. Okay, so how this function will work? So add node will accept three things. One is a pointer to the array. Okay, this is array pointer. One is a pointer to array. So in this program, what we are doing is we are passing an array and building a tree for the array. Okay, so this is array that I have declared, and I'm passing this entire array to the function and forming a tree for the function, and I'm adding a printf statement here that at each step what all elements we are adding, so that we can know which element is added at what preferences. So this is the uh, left index of the array, this is the rightmost index of the array. Okay, so this is a recursive function. In binary trees, if once we should be very good in recursions, because most of the solutions or most of the problems that we do in binary tree can be solved easily by recursion. Okay, so let's begin. So first we have an exit condition. That means if left index is greater than right index, then we will exit and return null. Then we will calculate a mid equal to left index plus right index by 2. So we will get a center index, and then we will assign it as a as a parent or root node. So we will assign a memory here, and then we will add the values. Say we will assign extra data equal to the mid value of the array. Then we continue building the left subtree first. How we are building left subtree? We are passing the index, what is the remaining part of the left subtree, which is left and mid minus 1. Okay, and we will build a binary left binary tree, and then we will build the right binary tree. So how we will build the right binary tree? We will build the right binary tree by passing the remaining portion at the right side of the list, like this. And now we are using this in our main function, which returns a root node, and this root node will be our primary node to work with. Okay, so this is how this program will create a binary tree and return a root node. To be more specific, this program will create, or this function will create, a binary tree out of a given array, and return the root of the tree. So let's try to compile and execute this program. Okay, gcc minus o tree binary tree.c. So we got a compilation success. Let's run it. So this is how we are getting the output. First 5 is added, then 2 is added, then 1 is added, then 3 is added. So we are adding the left, first we are adding all the left portions. So first 5 is added. So whatever what all are remaining in the left side of binary tree or left side of the array is 1 2 3 4. Okay, then 2 is added. Okay, because we pick one element as a root, so 2 is picked as one element as a root, and then left side of 2 will be added, which is 1. Then left, there is nothing on the left side of the 1. We will go whatever is the right side of the 2. So right side of the 2 is 3 and 4, so 3 and 4 will be done. So this is how we build the left tree. Then we reached 5 again because it's a recursive function, and then after once we reach the root node, we will try building whatever is the remaining at the right side of the 5. Okay, so right side of the 5 is 6 7 8 9, so we'll follow the same approach and we will end up building a binary tree. Okay, so this is our output, and this is how elements will be added. Okay, let's continue. So tree traversal, what do you mean by tree traversal? So tree traversal is like how we are traversing in the tree, or how we are um, print, if you want to, if somebody gives a question how to print values in the binary tree, so how you traverse the tree. Okay, so there are many ways to walk through the tree or traverse the tree. Okay, so tree traversals are naturally recursive. So uh, we whatever approach we will be following on for traversing the tree, it will be a recursive approach. Okay, since a binary tree has three parts, one is root, left, right, there are six possible ways to traverse a binary tree. So there are, what all are the ways? First we traverse the root, then we traverse the right child and left child. So left child and right child are like left subtree and right subtree. Okay, so when in the traversing terms, what if we say left, that means always a left subtree and right subtree. Okay, so here first we are traversing root, then the left subtree of the root, then the right subtree of the root. Left root right, that means first we will traverse the left subtree of the root, and then right subtree of the root. So what all the combinations we can try, and this will become, this is, it depends upon what is our problem and how we want to solve the problem, and what approach or what kind of traversal technique will be good to do. So let's see three very important traversing techniques. Okay, and we will be using flag method to solve it or to traverse it. So in order, the order in which nodes are visited during the tree traversal can be determined by imagining there is a flag attached to each node as follows. So this is a pre-order, this is in order, this is post order. So pre-order means uh, first we begin with the root. Okay, in order means first we begin with left subtree of the root, then root, and then right subtree. Post order means first we uh, begin with right subtree of the root, then we come to the root, and then left subtree. To traverse to traverse in above 3 order, we need to collect the flags. So if we traverse this way, like try from start from root and start collecting flags, so we will end up in this path. We will go from A to B, B to D, and D to E, and then A to C, F and G, like this path will follow. So what is this? This is a pre-order traversal where we traverse the root first and then the left subtree, then root first, then left subtree. Once it is done, then right subtree. Okay, and so pre-order is nothing but traversing the root first, then the left child, and then the right child. In order, in order is traversing the left child first, and then the root, then the right child. So this is how we do the in order traversal. We visit left subtree, we complete the left part of the tree, then we go to the root and then complete the right part of the tree. Post order traversal. In post order traversal, we complete the right part of the tree first, then we go to the root and then we complete the left part of the tree first. Okay. So let's do some practice. Write a program to create a binary tree from a given array. So this we have already completed. We just did one program which creates a binary tree from a given array. I'll advise you to try this program on your own without going to the code that I have given. In case you find any difficulty, just go back to the code, refer it, and try it on your own so that you can get more expertise. Write a program to find a specific element in a binary tree or binary search tree. So let's write this code. Let's try to solve this problem. So this is a very simple code to create a binary tree out of given array, and find a particular element in the binary search tree. Okay. So again we are having the same kind of structure where we are having integer data and then left reference and right reference. We are having two methods. One is add node to BST, which will create the binary search tree. Okay, and we will have one function which is called find value. So this function will give us 0 or 1. If 0 is written, that means the value is not found in the binary tree, and if 1 is given or 1 is returned by this function, that means value is found in binary tree. Okay, let's try to see what these functions are. So add node to the BST is a function. So this is add node to BST. This function will create a binary tree. Okay, and this is a recursive function. So uh, whatever first we need to give a root pointer or reference to a root pointer, which is address to root pointer, and a value that what we want to add. And this function first check if root is null, that means our tree is empty. What it will do, it will just assign or create one node, fill the value, that data part equal to val, left child equal to null, right child equal to null, assign the root to this value, like x is assigned to root. Okay, and return it. In case if root is not equal to null, then we will say if value is, or whatever value we want to add, is greater than the data part. Okay, If value is greater than the data, then we need to add the element at the right. Okay, and if the value is less than data, then we need to add the element towards the left. Okay, so here in case we found any value which is greater than the root, then what we are doing is we are again doing a recursive traversal, or we are again calling this function with the with the right child of the root node and adding this value to the right subtree. Okay, and in this case we are adding the value to the left subtree. So the value will be added at the leaf part, so it will keep on traversing till we found a exact condition, and then we will add the value. So in main function, how we are using is, in main function we are declaring one array. This is how the array is declared, and then we are running a loop. Okay, first we are having a root pointer declaration where we are declaring bst equal to star root, where we are declaring a pointer variable to this structure and assigning it to null, and then we are iterating through the loop and adding this value. So this is an unsorted array. Okay, and we are creating a bst out of it. So once the root is created, now what we are doing is we are using a find val function. So let's see what find val function does. Now the find val function will find a particular value in the binary tree. If a value is found, then it will return 1. If the value is not found, then it will return 0. Okay, so if the root is null, it will return 0. If value is found, like if value equal to root dot data or root arrow data, then we return 1, that means we found the value. Otherwise, what we will do, if the value is less than root data, then we will go to the left portion of the binary tree. If value is greater than, that means it will come into the else condition, then we will go to the right side of the binary tree. So this is iterative function where find val is called itself, and we will be returning some value. So where we are returning the value, if we find any element which is null, like we are traversing and we didn't find any element, we will return 0. In case if we find the element, we will return 1. And return type is equal to, we are always returning an or value. That means if nothing is found, we will returning 0, because 0 or 0, 0 or 0 is equal to 0 only. And if something is found, we are ORing that value with 1, that means final result will be 1. So this function will return 1 when anything is found, or whatever value we want to search is found in the binary search tree. If the value is not found in the binary search tree, we will return 0. Okay, so let's see how we are using this in the main function. So in the main function, let's declare one variable int x equal to 9. Okay, now we are declaring one more variable, say v, and calling find val function, like what if find val function is returning any value uh, for 9 or not. We are comparing, if v equal to 0, that means value is not found. If v equal to 1, then value is found. We are using a conditional operator here. Now we are again assigning x equal to 78 and saying that okay, if value is found or not. So let's try to run this program. ECC -o bst.c. Okay, we got compilation success. Let's run this program /bst. So this is the output. We have added all the values, or all the uh, elements in the array. Then we searched 9. Once we searched 9, we got 9 is found. So yes, 9 is present, 9 is found. Then 78 is not found. Yes, 78 is not there in the list, so 78 is not found. So this is how searching in binary search tree works. Again we go. So if the root is null, that means that it is not, the value is not present. If value is equal to the data present in the root, that means value is found. If value is less than whatever is data present in the root, then we need to go through left subtree. If value is greater than, that means else condition, then we need to go through the right subtree. So this will reduce our scope of search and will help us out in enhancing the search performance. So I suggest you should try this program at your own and try some different variants, like you can try out having a larger array and creating a binary tree from it, and then you can have instead of declaring whatever we want to search here, you can get value from user and do searches and all. So you can just try out and do as much as practice as you can, so that you can get more and more hands-on practice on binary search tree, because binary search tree is a very important data structure, and understanding this data structure takes some effort. It's not an easy data structure to understand. Only you need to do a lot of practice to get mastery over binary search tree. So there is one more program that I want you to try on your own. Write a program to print in order, pre-order and post-order traversal of binary tree. Uh, this is also fairly simple program once you get mastery over binary trees. Uh, just try it on your own and try to do as much practice as you can.
I'm sure you enjoyed learning from this video. Please like the video, and if you have any doubts regarding this video, please comment us in the comment section, and don't forget to subscribe to our channel for more such informative videos. Do look out for other related videos in our playlist. For more information, visit our website now. Keep learning with Intellipaat.